this brief introductory video, I'll explain how to use the Asteroid Institute's Trajectory Optimizer service to compute transfer trajectories between solar system bodies using Lambert's problem solver. This tool can be used to plan spacecraft missions, analyze asteroid deflection scenarios, or explore transfer opportunities between any two bodies in the solar system. Whether you're looking at interplanetary transfers or more complex rendezvous scenarios to a near-Earth asteroid, the service provides the detailed calculations to find an ideal launch window. To access Atom Trajectory Optimizer, go to b612.ai, click on the Atom Platform dropdown, and select Trajectory Optimizer. To get started, you'll need to specify two things: your departure body in your departure window, and your arrival body in arrival window. First, let's talk about selecting bodies. We provide access to bodies from multiple sources via the drop-down menus. SPICE provides high-precision ephemeris data for planets and major bodies. We've included the planets and the 16 most massive asteroids via SPICE here. You can also specify a departure-arrival body via JPL's small body database or Horizons. When using either of these, you can search by IAU number, designation, name, or SPK ID. Use Horizons if you would like to rely on the body ephemerides generated by Horizons. We use the assist propagator to compute the arrival body state for state vectors pulled from SPDB, or from our third source, ESA's NeoCC. Please note that because we use the assist integrator, you'll have to use the SPICE definition or Horizons for the 16 most massive asteroids, as their gravitational contributions are considered in assist. After making your selections, and we'll put Eros in here as a test, you'll see a confirmation message showing the bodies were found successfully along with their source information. When selecting launch time windows, you can specify these using either a date picker or more directly using the modified Julian date if you need more precise control. The date format shows your local time for convenience. And here let's go out to 2028 for launch and 2029 for arrival. This is giving us about a 3-year range on either end. After body selection, there are a few more settings to go through. We allow you to switch between prograde and retrograde transfers, though which of these produces better results will depend heavily on the particular departure and arrival bodies. The step size is determined automatically based on the date grid chosen. It's set to the max granularity that we support for that date range. You may consider running a wide time range to start and then picking a time region of interest to rerun at higher granularity. Finally, if you want to limit your search to specific energy requirements, you can set constraints on C3 departure energy and V infinity arrival velocity. These help filter results to realistic mission scenarios. And these aren't set by default. There's a 200 maximum C3 set, and that's good for many use cases. Once you're done, hit Calculate Trajectory to start your analysis. Now, on submission, you'll be taken to a loading page showing your job information and transfer parameters. You'll see details about your selected departure and arrival bodies, including their sources and the time windows you specified. As the computation progresses, you'll see status updates. The page automatically checks for updates and will show the results when they're ready. A typical run can take several minutes, depending on the complexity of your transfer and the time spans chosen. You can bookmark this page and come back later. The job will continue running even if you close your browser. Now let's look at what your results will look like and how to interpret them. First, you'll see a summary of your job parameters, the departure and arrival bodies, time windows, and transfer settings you specified. The centerpiece of the results is the porkchop plot. This interactive visualization shows departure dates on the x-axis and arrival dates on the y-axis, with contour lines representing different energy requirements for each transfer opportunity. There are actually 2 contour plots overlaid here, though only the C3 plot is displayed by default, and you can switch between them by clicking on these buttons. The plot is fully interactive. You can hover over any point to see a quick preview of the transfer parameters, including C3 departure energy, V infinity arrival velocity, and time of flight. You can also box select a region to zoom, and there are other controls on the right, up here, where we can go back via autoscale. You'll see 2 points with special badges: optimal C3 solution for the most energy efficient departure, or optimal V infinity solution for arrival that minimizes V infinity. Just be aware these are optimal within the time ranges you picked. When you click on any point in the plot, you'll see detailed transfer information appear below, including the complete transfer timeline, energy required, and orbital elements. A circular marker shows your position on the plot. The transfer details show everything you need to know: departure and arrival dates, the duration of the transfer, energy requirements like C3 and V infinity, and the complete orbital elements of the transfer trajectory. You'll also see state vectors and direction information for both departure and arrival. For convenience, all of these can be copied to CSV. Just note that all downloads and the CSV copy provide higher precision than the truncated values displayed here. Below the porkchop plot, you'll find an interactive 3D visualization of your selected transfer. This shows the actual trajectory in space, with your departure body in blue, arrival body in red, and the trajectory solution in green. You can rotate by clicking and dragging, and zoom in and out by scrolling. Hitting the play button will animate the transfer from launch to arrival. You can also click or drag the progress bar to go to a particular point in the solution. The visualizer does struggle with hyperbolic orbits, so those may not display if you, for example, plan a transfer to an interstellar object such as Oumuamua. So let's say you found a good trajectory and want to drill down deeper, or you want to dig into the Lambert results or do some of your own plotting. All of the raw data are available for download in multiple formats. The detailed Lambert solutions are provided as CSV files with additional data including departure and arrival body states. We also provide the Lambert solutions in Parquet format for analysis with our open source Python tools. We recommend using Atom Core to look at these files. There's additional functionality such as methods to compute C3 and VINF, and manipulating solutions as qualified orbits. Those are only available when consumed this way. You can also download ephemeris files for both bodies in standard OEM format, and get a standalone HTML version of the plot for portability. Just like our other services, the underlying code used for this tool is open source through our Atom Core library, and we invite technical users to try it out for themselves. We have a simple code snippet here that shows you how to get started with analyzing the Lambert solutions with Atom Core. Thank you for taking the time. If you have questions or need support for more complex scenarios than we currently expose in this demo, don't hesitate to reach out to our team. Just click on the contact link above and shoot us an email. And if you would like to stay in the loop about future services and feature updates, please subscribe to get notified when those are ready. Thank you.